Right. I don't know what the time is. Are we live? Okay. So let's get started, and as people walk in, we'll make sure they get caught up. My name is Aashish Parikh. I'm an engineer. I work in the DRS team. I've worked here for 3 years now in the DRS team, and I've worked at VMware for 8 years, so 5 years before that in the hypervisor team. I've worked on DRS, storage I/O control, distributed power management, resource pools, affinity rules, the whole set. So if you have any questions, we can talk about them after the talk is done. The other versions of this talk took the whole hour, but I'll be around after the talk is done, so if you have any questions, come up to me and talk to me. I have my business cards here too, so if you guys want to grab one, send us any questions you have or any comments or feedback, we'd love to hear from you. There are a couple of times in the talk where I'll ask you for feedback, or I may ask you if you have that problem, and if you're able to share some files with us, share those files with us, and again, get my card. Some of the topics I may not be the world's greatest expert on. I'll find you the right person to talk to. All right. So this talk is titled New Features, Best Practices, and Future Directions. It's basically new features in vSphere 5.5. I wasn't allowed to put that in the title because when I made this talk, we hadn't announced vSphere 5.5 yet. Right? But that's what the new features are in. Before I get underway, we gave a talk last year at VMworld, but it was only in the VMworld US, titled DRS, Advanced Features, Best Practices, and Future Directions. Have any of you seen a video of that? Maybe, yeah, 1, 2, okay, a few people. I have a link to that in my talk today, and the only reason I mentioned that is because we took the time in that talk to go into a lot of details into some of the things that we're going to go over in summary form today. So that might be something that you might be interested in, might be something you want to look up. All right, so let's get started. Given that we're heading towards late Thursday, I'll wager that all of you have seen this disclaimer a few times by now. It's something our legal team makes us do. Basically, anything we talk about, especially things that have got futuristic undertones, we can't associate a release with them. We can't even promise you that they will come out. But your feedback helps. It helps influence the direction we take. It helps us prioritize the features we have. So please keep that coming in. Here's the general overview of the talk today. First, we'll talk about some advanced resource management concepts, specifically VM entitlements and happiness and load balancing in your cluster. We'll then talk about the new features that have been introduced in vSphere 5.5. And what we did here is basically took a list of several hard problems that we've heard about in small or big ways over the years and gone after them. A lot of the low-hanging fruit we think we've covered. We're going after the really hard problems that are left to be solved. Finally, we don't innovate in vacuum, right? And DRS is not an island, so the rest of VMware is innovating too. And when those features come out, we want you to try those features. But a lot of work has to go on in the back end to make sure that you don't have to give up DRS to try those features. So we'll tell you about how DRS plays nicely with a whole bunch of new features that have come out in vSphere 5.5. Right? And finally, what all of you are here to really see, I know, is a sneak peek into our labs. We'll show you what we've got cooking, what's coming up, and that will give you both a hint of the direction we're about to take and a chance to influence it, right? Couple of other talks at VMworld that were DRS and storage DRS related. They're all done, so you can't attend any of them now. But once you have the deck, you can actually look at their videos. They should be available to you for viewing. The people who gave these talks, they're my friends, my colleagues, my team members. They wrote the code along with all of us. We did. But they introduced all the bugs. So if you have any bugs to worry about, go talk to them. Send them email. The 2012 talk is the one I was alluding to. It's got video in the slides. And finally, we have some tech journal papers for any of you who are more academically inclined, or if you want the nitty-gritty. We have one on DRS, one on storage DRS. That will help you really understand what we're doing. So let's get started. Let's talk about contention of VMs for resources. Let's talk about happiness of VMs. Let's talk about how constraints are handled and how load balancing is done in a cluster. The key abstraction that DRS likes to provide its users is this notion of a giant host. Right? You have a bunch of hosts, bunch of very real machines in your data centers, and we'd like to think of you as one, we'd like you to think of those as one continuous pool of cumulative capacity, right? Just one set of one big host whose capacity is basically the sum of the capacities of all the other hosts. Right? This lets you manage one big host instead of having to manage 10 or in some of your cases 32 hosts. And why do we do this and why is this hard? We do this simply because it makes management easier. right? But why is it hard? It looks like a pretty obvious thing. Fragmentation is what makes this problem a very hard problem to solve. A VM cannot straddle hosts. You can't have a VM live half on one host and half on another, right? And that makes the problem of actually implementing your giant host abstraction a very hard problem to solve, right? And what is the goal? While we are trying to decide which VM must live on which host to give you that happy illusion of a giant host, right? What is the primary metric we're looking at? The primary metric we're looking at, and this is the key point of this section, is VM happiness, right? Believe it or not, everybody thinks of DRS as a load balancing engine. That's the most visible feature we have, and we'll talk a lot more about that too. But DRS is really a VM happiness engine, right? That's what we strive to do. And we define happiness, right? We actually have code that uses variables called happy, right? So we actually know whether a VM is happy or not, and we can do things to make it happier. How do we define happiness? We define this concept called entitlement, which is basically a number that we think your VM is entitled to. You have a VM, which may have several resource control knobs in it, reservations, limits, shares, etc. And your VM has demand. It demands certain amount of CPU cycles, certain amount of memory cycles. And this happens across all the VMs in your cluster. And based upon all of these numbers, we compute for every VM a certain entitlement. We tell this VM, I think you're entitled to 1.2 gigahertz. I think you're entitled to 2.4 gigahertz, right? And if we can put this VM onto a host where it can actually get those cycles, that VM is said to be happy. Right? That's how we define happiness, and that's our primary goal. We want to make VMs happy. Why is this our primary goal? Why is keeping VMs happy so important? So we believe that all things being equal, VM happiness translates to application happiness. If you've configured your VM so that your application can live nicely within your VM, then giving your VM whatever it wants means it can give the application whatever it wants. Right? So that's the main intuition here, that the closest proxy we have today for application happiness is your VM happiness, and we strive to do that. And why is this not met by default? Sure, we understand what entitlement is, we understand what happiness is. Why is it so hard? Simply because one host might have too many VMs in it and may not be able to meet all of their entitlements with its finite capacity. So in general, when a VM is unhappy, it wants more resources, right? And how do you give it more resources? How do you give it more capacity? There's three ways in a cluster to give it more capacity. The easiest, cheapest way is to give it more resources from the same host that it's already on. You basically steal resources from another VM that might be consuming those resources, or another set of VMs that might be consuming those, and give those resources to this VM, and you make this VM happier. Right? But you might run into a situation where you've got too many VMs on the host. You can't steal from anybody anymore. Right? Or all those VMs are equally or more important than you are. So you can't steal any more resources from your neighbors, immediate neighbors. So what do? You go to another neighborhood, right? You can actually take this VM and vMotion it to a different host where you will have that capacity that you can use. You can keep doing that for a bit, and soon you run out of capacity in your cluster. You don't have any more hosts that are good candidates, right? And if you're using DPM, some of you are, and they'll tell you all about the wonders of it, right? You can power on some hosts that might have been put into standby mode earlier, and those hosts now become good candidates for these VMs to go, and their capacity can be increased that way. So these are the three ways in which you can actually provide capacity to a VM for it to meet its entitlement. And note that demand is not the same as utilization. A VM can demand a lot more than it's currently using. It might actually have a lot more work that it's willing to do given the resources. Right? So we've been talking about load balancing. Why not use load balancing as our primary metric? Why not be a load balancing engine? Why not always try to keep your cluster perfectly balanced? Why is that not our primary goal? Right? And there's one simple reason for it. The simple reason for that is that load balancing doesn't come for free. The migrations we need to do in order to load balance your cluster cost your VMs some resources. It takes a few cycles for a VM for its working set to be moved over from one host to another. There is a tiny amount of downtime that your applications will notice. It's not that we make it as transparent as possible from a correctness perspective. You shouldn't lose transactions, but they may become slower, right? So it is a cost that we try to avoid if we don't have to incur it, right? If you have VMs that are all idle, that are not doing much, there is a very finite amount of cost associated with moving a VM from one place to another. But this VM didn't want anything on the source, and it's not likely to want anything on the destination either. So there's really no benefit here, and our cost-benefit analysis will filter such moves out. right? The best way to think about load balancing that DRS does is as a mechanism to guarantee the primary metric, which is VM happiness, right? When you're trying to make a VM happy and you want to move it, let's move it in a way such that the cluster remains load balanced. When you're trying to place a VM, where do you want to put this VM? Let's put it into a place such that the whole cluster is load balanced. And this load balancing is a lot more complicated, and we have a bunch of slides about it too. So hold on for a few more details. But this is the best way to think about load balancing. So just to illustrate this example, imagine a scenario with 4 hosts in a cluster, and you've got these VMs, and imagine that they're all identical VMs, right? And imagine further that they're all almost idle VMs. They're doing nothing, and they're getting whatever they want. The question is, should we balance these VMs? There's definitely an imbalance here because there's different numbers of VMs on different hosts. Is it obvious that we should balance this cluster? The answer is it's not obvious, right? There are cases where you may have a really quick network, and it might cost us next to nothing to migrate and actually fix your imbalance, and we'll do it. We actually model how quickly your vMotions will happen and take that into account while deciding whether or not to make a vMotion, right? So if you, and then there are several cases where that vMotion might be so expensive relative to how much benefit it can get you, right, that we may not recommend it at all, right? This is what we'd like you to look at. You can go to your monitor tab and look at CPU and memory utilization here. You've got little Gantt charts, kind of charts here. This basically tells you about a 4-node cluster, 4 hosts in your cluster. Each row there is a host, all right? And within each row, each of those green boxes represents the entitlement of a VM, right? The first host has 3 VMs. The second host doesn't have any VMs. Third one has 4, and the fourth one has 1 gigantic VM. The width of that rectangle represents the entitlement of this VM, right? Clearly, this cluster is not balanced. If it was balanced, all the green bars would line up, right? Or be pretty close to each other. And they're clearly not that way here. The most important thing about this picture, though, is the color. The fact that they're all green, they go all the way to red, means that these VMs are meeting their entitlements. Note also that the 4th VM, the VM on the 4th host is so big that no matter where you put it, you're going to have an imbalance in your cluster. It's mathematically impossible to balance this cluster, right? You can put a sumo wrestler on one side of a seesaw. It doesn't matter how many little school kids you put on the other side. Not going to work, right? So you can see that the load is not balanced in your cluster, but all your VMs are happy, right? Given that we've been talking about load balancing, I've discovered that a lot of audiences appreciate understanding the nitty-gritty of this. So I'm going to explain load balancing that we do in DRS to you guys by explaining a simple math optimization computer science problem that's well understood. It's been studied for 50 years, which is the age of computer science, I guess, right? It's called the balls and bins problem. You've got n balls and m bins, right? And you have to decide which balls go into which bins. Fairly straightforward, right? Except the balls can have different sizes. Some can be bigger, some can be smaller, right? Some can be blue, some can be green. They can all have different characteristics and different meaning behind those characteristics. The bins can have different sizes. You can have a much bigger one. All of them can have different sizes, right? There's no homogeneity that's required. And the sizes of these balls and bins can change dynamically. Imagine every second that you could have a bigger one go smaller, a smaller one go bigger, and this could apply both to the spheres inside or to the bins, right? Either of them could dynamically change. And imagine you were allowed to specify constraints on how these VMs are placed or moved, or how these balls are placed or moved. That these 2 blue ones must never move unless they move together, right? Or the red one must always live in bin number 3, right? Or these 3 green ones must always live in any of these 2 blue ones, or in any of these 2 bins, right? So there's a whole bunch of co-location constraints that can be placed that make the problem of distributing these balls across these bins a very hard problem, right? And this is the problem that DRS load balancing tries to solve. Right? The VM resource entitlements we've been talking about so far are your balls in this experiment, right? And the host resources, the capacities that you have, are your bins, right? It should be pretty clear to you that load can change dynamically, right? An application can want more things at some time and less things at another, so the size of the ball can change. But so can the size of the bin. VM kernel, which is our kernel that lives inside ESX, is a pretty sophisticated creature. Right? And it will only take up as many resources as it really needs to and leave everything else as capacity that the VMs can use. Right? The problem with that, though, is that the amount of capacity available to the VMs, the bins, keep changing their size, right? And that makes this problem a very hard problem to solve. We also have a whole bunch of constraints that we let you set on VMs. You can say DRS should be disabled on this VM, don't move it around, right? Or you can actually say these two VMs must always live together. They have an affinity rule, right? Or these ones must never live with each other. So use these affinity rules, use these business rules and constraints. They're all valuable business tools. If you have a use case for an affinity rule, use it by all means. But realize that doing so places a constraint on the load balancing problem, right? The goals of the load balancing problem, the first one is fairly obvious. We want to make sure we fairly distribute the balls across the bins, even if they have different sizes. Note that they all have approximately the same y-axis, right? They're all the same height. They're all being used at 70%, maybe. Enforce constraints. In a lot of ways, this rule or this goal is even more important than the first one. When you tell us that a VM must live on a certain host, we will actually make that happen first and then do load balancing the best we can from that starting point. We will not violate your constraint in order to make the cluster better load balanced. Right? So like I was telling you, realize that setting more and more constraints can make the load balancing problem harder and harder and set impractical or sometimes impossible targets for DRS to achieve. DRS recommends moves that significantly improve your cluster's balance, right? We don't want, given a choice, we'd rather not pick a drop in the ocean kind of moves. We'd rather not move VMs which have tiny entitlements around. We'd rather move one big VM that substantially addresses imbalance in your cluster. And we have customers who come to us and tell us, I have so many VMs, why are you moving my big one? Usually big ones are also their important ones, right? The reason for that is DRS takes into account all your 4,000 VMs that are in your cluster at that time and holistically decides that making one move here is better than 100 other moves that I need to make to give me the same bang for the buck, right? We also recommend moves with long-term benefit. We don't want to make a move and then realize, oh, I got to move this VM again. So we make moves which we think will have validity for about an hour, right? For about 1 hour, these moves are going to remain valid, and we make moves with that intention in mind. Finally, in your UI, you'll see this little spirit level bubble thingy move all the way from imbalanced to perfectly balanced, right? You'll actually see this. We've been talking about more imbalance and less imbalance, better and worse imbalance. How is imbalance measured? What is an imbalance metric, right? It's a cluster level metric. That's the first thing you want to keep in mind. There's no notion of a VM being imbalanced or even a host being imbalanced. There's only the notion of a whole cluster being imbalanced, right? And how do we measure it? There's a tiny amount of math here. Don't worry about it. Very simple, right? You've got 3 hosts, and we compute this notion called normalized entitlement, which is basically geek talk for how much of this host is used up, right? The first host is used up 65%. The second host is used up 10%. The third host is used up 25%, right? And then we compute a number called standard deviation, a function called standard deviation on these numbers. This is a very basic statistical quantity. You guys might remember it from your stats class. It just tells us how far apart these numbers are from each other. What is the variability, right? And this lets us know whether or not your cluster is balanced. The cool thing about standard deviation is it's either 0 or it's a positive number. It's never a negative number. And 0 means your cluster is perfectly balanced. Right, you've got an identical set of hosts and VMs, things are perfectly balanced, and things are going fine. The problem is that this is pretty ideal. You almost never get something that's 0, right? And you can take a few VMs out of one of the hosts, and you're not balanced anymore, and you can take a few more out and a few more out, and there is no upper limit to how imbalanced you can be. Standard deviation can hit infinity, right? There's no real upper bound to it. The lower bound is 0. So the real question becomes, how much imbalance can you tolerate in your clusters, right? In your cluster, what is the level of imbalance you want? I've had customers tell me at this point, well, how the hell should I know? How do I know how much imbalance I can tolerate? That brings us to this topic I like to call the myth of target balance. We have this little slider in our UI, and you can move it around. It's usually bang in the middle of conservative and aggressive. I've only moved it to the aggressive side to show you that it can be done. It's not an editorial, so don't go into it. Let it sit in the middle. For most of you, for most of the time, that's perfect, because we do a lot of testing with that, right? But what does it mean to move it around, right? And I'd like to tell you about that a little bit. There's some math here which I'm not going to go into. If you want details about it, write to me, and I'll send you a knowledge base article we've written about it, which will give you all the details. But very, very simple terms, what it means is if I have 2 hosts in my cluster, moving my slider to the first notch tells DRS I'm willing to tolerate 10% standard deviation in my cluster. If you move it to the second one, it's 20%. You move to the third one, it's 30%. As simple as that. Right? By default, if you have 2 hosts in your cluster, you're willing to tolerate 30% imbalance in your cluster because that's where the slider sits. As you add more hosts to your cluster, we change that number dynamically for you, and all those details are in that knowledge base article. Right? As we've discussed before, constraints can make it hard to meet your balance, right? It may make it hard or impossible to meet the number that's implied by your slider setting. So when you make something more aggressive, when you make it more aggressive than conservative, what you're doing is increasing the bar that we need to cross to call ourselves balanced. From the setting 3, if you move it to 2, you're basically saying, I cannot tolerate 30% imbalance in my cluster, I can only tolerate 20. And in order to make that happen, we'll do a whole bunch of vMotions. So it may be possible to achieve a more aggressive target balance number, but realize that doing that might require a whole bunch of vMotions to happen. Right? The only way we might be able to meet it is if we do hundreds of vMotions in a big cluster. The one line I'd like you guys to take away from this section of the talk, if you forget everything else about this section, is this, right? If all your VMs are happy, if they're getting what they want, a little imbalance is not a bad thing in your cluster, right? So let's wrap up this section. The goals of DRS are to provide a giant host abstraction to meet VM entitlements and make sure that they're happy, and to use load balancing as a secondary metric to make that happen. We're always recommending moves that are improving the entire health of the cluster as a whole, your imbalance of your cluster. Constraints can make it really hard to achieve some targets. And if all VMs are happy, a little imbalance is not a bad thing. So let's talk about the new features that we've introduced in vSphere 5.5, right? The first one I'd like to talk to you about is restricting VMs per host. And let's talk about this by going through an example, right? Imagine you've got this cluster, it's got 4 hosts and a bunch of VMs scattered around, and imagine that this is perfectly balanced with respect to CPU and memory. All the VMs are getting what they want, right? That's your starting point. And you've got a whole bunch of VMs that are coming in to your cluster. They need to be powered on. Because the 4th host, as you might be able to see from the diagram, is much bigger than the other 3 hosts, it's ideal for the new incoming VMs. I'd love to put all the new incoming VMs there, right? But spreading VMs around is important to some of you. You guys have business cases that require you to, restrict the number of VMs that die if somebody trips over a wire, right? You don't want to put too many VMs on one host, even if it's a bigger host, right? And there may be licensing reasons you guys might want to spread VMs around. So we introduced an option for you in vSphere 5.1 called limit VMs per ESX host. Now, if you had set that number to 6, instead of putting all the 4 new VMs on the big host where they would have been best placed, we place only 2 of them there and find other places for the other VMs. So now we've respected that constraint you've set on us, and we've only put 6 VMs on each host. DRS will not admit a 7th VM on any of these hosts. It will not migrate a 7th VM to any of these hosts, right? But there's an obvious limitation here. Your big host is locked out for new VMs. You can't really put any more VMs onto it. It's a beefy host. You can put 10, 20 more VMs there, but DRS won't let you, right? Because we're respecting that property of yours. And this number, the fact that it has to be managed manually, you have to go and bump it up, bump that number up to 8, bump that number up to 10, bump that number up to 12. That's not the way DRS likes to do things. We prefer that things are zero-touch management, absolutely no overhead for you guys. So we've added a new option in vSphere 5.5 where we auto-tune the number of VMs per host for you. I'm going to have to read this option. It's called limit VMs per ESX host percent. I know it's a long name, but all the good names were taken. So we kind of had to pick this one. Right? So let's walk through an example. Imagine that this 20 VMs in your cluster right now, and imagine you've got 12 more coming in. So you're going to have a grand total of 32, right? Ideally, because you want to spread them around, you want 8 VMs on each host. You want to spread them out, right? The mean, the average is 8. But if DRS went ahead and automatically used this information to set that number at 8 for you, you run into a similar problem like before where no load balancing is possible anymore. If everybody has 8 VMs, any load balancing move makes somebody have 9 VMs, right? And that will basically disable your load balancing entirely at that point, effectively. So what you want to do is use this new option to give us a little buffer around the mean that we can use as a little leg room to actually move VMs around. So let's imagine that that number given to us was 50%. So what DRS will do is automatically take the mean, compute the mean, and add the buffer percent times the mean to the mean and use that as the limit. In real numbers, your mean was 8, right? 32 VMs, 4 hosts. Your buffer percent was 50. So 8 plus 50% times 8 is 12. So we set 12 as the limit on all these hosts, right? And that means your big host can be used much more effectively. It can take in a whole lot more VMs than it could earlier, and it lets you get the most bang for buck from your big hosts. One thing to keep in mind is that this will not fix any existing violations of that rule, right? So if you already had 20 VMs on a host, we're not going to fix that for you here. But we'll make sure that you're not, whenever you power on a VM or migrate a new VM, this rule is going to be enforced. The next feature I'd like to talk to you about is support for latency sensitive VMs. So we've done a lot of work in latency sensitive VM support in vSphere 5.5. That talk was at VMworld Europe, and there were a couple others at VMworld US too. You should see those if this is important to you. The first thing DRS does when you mark a VM as latency sensitive from your config menu, you go to settings and say, oh, this VM is latency sensitive. What DRS does is it recognizes that this VM is latency sensitive. And with that, initial placement of VMs just works. You're not restricted to any hosts just because you're latency sensitive. We'll put you on any host, right? You have the run of the cluster. But load balancing gets a little smarter, right? We'll pretend that there's a soft affinity rule between that VM and the host on which it was placed. That makes it much harder to move that VM, right? Because as you might know, latency sensitive VMs are very sensitive to downtime, are very sensitive to vMotions, right? So this is something that we do automatically for you. And that rule that we set up is internal. We keep track of it internally. You won't see a new rule in your UI and wonder, when the hell did I put that rule in there, right? So the only time we'll actually migrate a latency sensitive VM is the only time we'll break a soft affinity rule, which is if you have a conflicting hard affinity rule, for example, that needs to be honored. And for that, we might have to break your soft affinity rule. Or if there is so little capacity that your VM is starving and we need to move it so that it can get some resources somewhere. All right, the next topic I'd like to talk to you guys about is ready time. How many of you have heard about ready time, have ready time problems, think you have ready time problems, worry that you might have ready time problems? Okay, so I see a sizable number of hands. This is a, we like to call this a Heisen problem. Every time we go to look for it, it goes away, right? And we've heard about this and seen this in several cases and tried to address every one we can find. Let me first define ready time, right? And I'm going to give you a very simple non-computer sciencey definition of ready time. Your virtual machines have virtual CPUs, right? And your real machines have real CPUs or physical CPUs, pCPUs. Whenever a vCPU needs to run, whenever it needs to do some work, it needs to be scheduled on top of a pCPU, right? So if a vCPU has stuff to do and we are not able to put it on a pCPU, that vCPU is said to be in ready state. I'm ready to do stuff. Why are you not letting me do stuff, right? And we keep track of how long each vCPU stays in the ready state, right? Because it's a direct measure of CPU contention. Too much ready time means there's a whole bunch of people waiting around for stuff to do, and there's not enough physical CPUs around, right? I'm not going to go over this diagram. It's a very common diagram you'll find in any operating systems, distributed systems book. It just tells you all the states you can be in. So there's several causes for high ready time, and we've already fixed a lot of the real problems we've found. But there's also a whole lot of myths and red herrings that we'd like to discuss today. So you can go back and diagnose your own setups and see if you're really running into one of those. When it's not, it's a false positive. You think it's a ready time problem, whereas it's not, right? So we'll go over some of them today. This is an active area of investigation because we're as tired as you are about the ready time problem. So we are trying to find dump files from problems that have been caught in the act. So Duncan helped us write an article, go to his website and submit VC support bundles and VM support bundles, and we'll look at them and we'll catch, if we catch the ready time problem, we'll fix it for you. So in this section, I'm going to go over some of what the common problems that we've seen, which are not really problems. I'm going to throw out the problem, and I'll see if anybody can guess what's going on or tell me what's going on. So the first kind of comment I've heard from customers tells me that, dude, my ready time number is 80%. That just can't be good. All my other numbers are at 1 and 2%, right? Is this a problem? How would you fix this problem? Does anybody know? Just raise your hands and chime in if you know. Yeah.
Depends on several things. It could be a limit, usually is, on VM or resource pool, or either the virtual machine needs more virtual CPUs than it has.
It needs more virtual CPUs than it has. That's true, but neither of them explains an 80% number, right? Any other guesses? We are actually going to get to those cases in just a minute. Yeah. That's a good question. So this number is a cumulative number, right? If you have an 8 vCPU machine, your ready time can be as high as 800%. Okay, this is something that's not usually known. It has historical reasons. It's a poorly named counter, but it goes back 10 years, and there's large amounts of code and solutions built on top of it. So if you have 80% ready time in a 32 vCPU machine, you have 2.5% ready time per vCPU. And we've noted, rule of thumb, up to 5% per vCPU is not a bad thing. Your VMs can usually handle it just fine. Right, so that's the first thing you want to check. Because people have a transient performance problem, they'll go to their perf charts, and the one number that pops out to them is, 80%, right? So that's the first thing you want to check. Next, my host utilization is really low, right? I've only got 20% host utilization, but my ready time is very high. What's going on here? Anybody? How about from this side of the audience? Yeah? You have a low reservation on the CPU? That wouldn't cause this. Yep, limit would cause this. Yep. Well, not DPM settings, but host power management settings, right? So you can go into your BIOS, and you can actually say, be really aggressive and save me power, right? And what your BIOS will do is effectively go power off half the cores to save you power, right? A whole bank can be powered off. What this means is in your balls and bins experiment, one bin just became half its size. And DRS has no clue about this. So we're just pumping stuff into it, thinking it'll work. Whereas now on that host, you've got too many vCPUs for the pCPUs. And something that this gentleman already alluded to, you can set a limit on your VM or on the resource pool in which that VM is. And that limit can say that this VM must get no more than 1 gigahertz of compute capacity. But your VM might want 2 gigahertz of compute capacity. And you've artificially introduced a glass ceiling on top, above which your VM can't be given any more, which means its ready time is going to start spiking up, right? So if you have high ready time, go examine your limits, right? If you're using limits, go see if you've got any limits set up. And finally, this one's my favorite. They say the host and the cluster utilization is really high, right? And my ready time is very high. Does anybody know what's going on here? Sorry? Overcommitment, basically physics. You need more capacity in your cluster, right? You just have too much stuff going on and too few physical cores to handle that stuff, which is why in every way you're being told that your host and cluster are overutilized, right? Your VC level alarms should have been warning you. If VC ops was monitoring your VC, that should have been telling you that you're running out of capacity, right? Next, we've got NUMA scheduler induced ready times. How many of you here don't know what NUMA is? Does anybody not know what NUMA is? Okay. Anybody else? Right. So to give you a very quick overview, it stands for non-uniform memory access. Most modern architectures are NUMA. So if you have 16 cores on a host, real cores, they may be split into 2 nodes, right, 8 and 8, such that the first 8 are much closer to one set of memory, and the other 8 are much closer to another set of memory, right? And the vCPUs, ESX is smart enough to take this into account when it's scheduling VMs to make sure that a VM which is put onto node 0 has most of its active memory, most of its working set in the memory that's closest to it, right? That lets that VM perform much better, right? And this can cause a ready time problem because you can have several VMs that can all have their memory sitting in local memory on the node 1, right? And nobody is using node 0 at all. So there's a whole bunch of cores that are empty or less utilized, and a whole bunch of cores that are more utilized. And you can see as a result of that you're going to have ready time because you've got a consolidation of vCPUs and pCPUs. So what's the solution here? How would you actually tackle this problem? Anybody have a hint? Yeah?
Don't have more vCPUs than you have cores on one socket?
You mean don't have more vCPUs than you have in one NUMA core, in one NUMA bank? That's possible, but that's not always a practical solution. What if my business requires it? The NUMA, to turn off the NUMA rebalancer? The problem is that we've seen that recommendation out in the public and we don't think it's a good recommendation. The real answer here is that there is no solution because there is no problem here. Right? There's absolutely no problem here, right? VC and DRS take into account the effect on CPU ready when they are doing this. Because while your CPU ready numbers are spiking up, your memory accesses are flying. Your memory is right next door. You don't have to go to a remote node to actually make a memory access, right? And for most applications, that's a much clearer win, right? So what we've discovered is that the benefit that you have because of NUMA scheduling, right, is directly more useful to you than the hit you might have to percent ready. If you had a percent memory ready, analogous to how you have CPU contention measured by percent ready, we have misrate curves and other things that approximate percent memory ready. Those would be doing much better, right? So net your application is winning. So there's nothing wrong here, right? Now to address what you just told me, there are a small class of applications which don't care about being close to their memory. They are very CPU intensive, they're worker VMs, they're stateless VMs, they're given a piece of work and they just go and do that work, right? Now if you have workloads that are like that, you don't care about memory access, you can turn off the NUMA rebalancer via some options, right? And that will help your percent ready, right? But it's not something we recommend unless you're really sure that's what you want to do. That's why we've not done it by default. All right, so I'm going to wrap it up by telling you how we've actually handled CPU ready for you. So far we've discussed problems and non-problems, but here are some solutions, right? In earlier versions of vSphere, till 5.1 I believe, we had some bugs, we had some problems where VUM and other update solutions, for example, could leave DRS clusters in a very severely imbalanced state, right? For maintenance mode, a whole bunch of VMs are moved out of a host, but once that host is back up, all of those VMs don't come back, right? And that can cause an imbalance, a skew in your cluster. And what that means is some of the hosts have a lot of the VMs, right? And that can cause ready time to increase in your cluster, right? So what we've done now is that DRS automatically detects and addresses aggressively severe imbalance situations, right? It's already checked into 5.1, vSphere 5.1, and it's been backported to a bunch of releases. So it's available in some update patches, right? And in 5.5, it should just work out of the box too, just like 5.1, where we'll automatically detect if we are in that situation and we'll do remediations to fix it. And if we fix the vCPU imbalance, we're improving ready time too. Next, how many of you have bursty workloads or think you have bursty workloads? You have high spikes in CPU requirement, but they only last for 30 seconds or less, maybe. Anybody? Yeah? Yeah? Some of you? Now, DRS is constantly monitoring your VMs, right? Through VC, we're always getting stats about it, but we're sampling it, right? And then we take averages of those samples to decide what your demand is. And we usually take 5-minute CPU averages, right? Over 5 minutes, what was your demand? And if you only had 1 or 2 tall spikes and the rest of the time your vCPU was doing nothing, the average of that might not look very tall, right? So in the balls and bins experiment, your ball might not really be bigger, as big as you might want it to be. It might actually be much smaller based on the average. So we've added a new option for you called aggressive CPU active. It's not set by default. So you have to set it to 1. If you do, we'll start taking a look at 1-minute averages instead of 5-minute averages. And that basically means we won't average out your bursts quite as much. Again, we don't think this is a real problem. We've only put it here because some customers think this might help them. So try this if nothing else works for you. And if enough of you tell us that this works, we might consider making this the default. We're also experimenting with several other techniques in our labs. Again, somebody mentioned you might have too many vCPUs than you need. Your application might only need 4, but you might have 32. And there's a fixed cost associated with keeping all those other vCPUs alive. And that can actually hurt your ready time. So we're working in our labs with some of those things to fix it up. NUMA aware DRS maybe. All right, so now that we've beaten the CPU contention topic to death, let's spend one slide on memory contention, right? Memory demand estimation. When you've got a VM, you configure it, you give it a size, and you say, oh, this VM has 8 gigs of RAM. That's the configured size that DRS sees. Now, during the lifetime of the VM's OS and the applications might only ever touch 6 gigs of it, let's say, right? That much memory is called the consumed memory, all the pages that have actually been touched, right? So we keep track of that. And then finally, we take a look at active memory, which is how much memory are you using right now, right? How much memory are all your applications using right now? And that active memory is going to be the size of the ball in your balls and bins experiment. That's your entitlement. And how does that number come to us? Oh, sorry. The little leftover yellow box, we call that idle consumed, simply because it's consumed memory, but it's idle right now. Nobody's using it. The active memory comes to us from ESX. Right? ESX does some statistics and tells us, oh, this VM which had 8 gigs of configured memory and 6 gigs of consumed memory has only 3 gigs of active memory. And how does it do that? It takes all the consumed memory that the VM has already asked for, and it goes and it takes a random sample of those and breaks up a bunch of those mappings and sees how quickly the VM wants those back. Right? So if you want 20% of your mappings back quickly, then 20% of your consumed memory is active memory. Okay, they do things which are a lot more sophisticated than that, so don't tell them I told you that they do just that much. I will be killed, right? But that gives you a general idea of how they estimate active memory, but we've discovered that that sometimes underestimates demand. So what we've done for you in 5.5 is given you a little burst protection. You see that little leftover yellow box, the idle consumed memory? By default, we'll take 25% of that and add it to your active memory as a buffer, and that becomes the size of your ball in your balls and bins experiment. Right? So you're a little more conservative with respect to memory. We're not going to hurt you with respect to memory when we move you around as much. All the VMs uniformly get this, right? But those which are least active today will have the most idle consumed memory left, so they'll get the biggest buffers added to them, right? If you think that that's not enough for you, you want to be even more conservative, you can turn that number all the way up to 100, right, using this new advanced option. And that will mean we'll basically take the whole yellow box and track your VM to consumed memory instead of active memory. This is uniform across DPM, DRS, load balancing, initial placement, everything now. Right? All right, so takeaway points from this section, number of VMs per host. You can tune that automatically, but use it carefully, please, because it affects load balancing and happiness. Latency sensitive VMs are effectively handled. We do better CPU ready time work with vSphere 5.5. We've got a new option. Use it if you think it'll work for you, but use it carefully. And if you run into problems, send us your descriptions. And finally, we've got better memory demand handling. Right? So let me just see how I'm doing on time. Perfect. 18 more minutes. So let me talk quickly about how we are working with other innovations in the vSphere ecosystem, right, with storage and networking features. The first feature I'd like to talk to you about is Vflash. You guys might have already attended some talks about this. You might already know a little bit about it. 20,000-foot view for those of you who've not yet seen those sessions. Vflash is basically a server-side caching solution that we've introduced in vSphere 5.5. You can create a VM, which will have virtual disks, VMDKs, and then you can say, you can statically define a reservation of Vflash for each of your VMDKs. You can say that this VM disk must always have a 1 gigabyte cache, which is stored in the flash, right? Which actually speeds up accesses to those blocks. This cache is a write-through cache. It's basically a read cache. And when you do a vMotion, these cache blocks are copied over to the destination for you, along with the memory that's usually copied over in a vMotion. We also copy over these flash blocks. So how does DRS play with this? DRS initial placement just works. Again, when you place a VM, you can place it anywhere in the cluster, provided the host you're placing it on has enough vFlash resources to guarantee your reservation. This works like any other reservation, like memory reservation or CPU reservation. Right? Admission control is going to use this. You're only going to be allowed to power on or resume on a host or be the target of a destination if your host can guarantee the same resources that the source host guarantees this VM. Right? Load balancing will work similar to latency sensitive VMs. We'll pretend as if it's soft or fine. We'll try not to move it, simply because if we had to move it, we'd have to move all the vFlash cache blocks along with this VM too. Right? We've got a couple of best practices for you. Use vFlash reservations judiciously. This is just good advice for any reservation. When you reserve something, you're denying that resource to others. Right? So don't go about, if you can, reserving 100% of your vFlash. That gives very little room for maneuverability. You can't actually move other VMs on. You can't admit any new VMs with those reservations. And in general, virtualization works best when you have different entities that want different things living together, so they can all share. Right? So try adding VMs that need vFlash and VMs that don't need vFlash together in the same cluster. That way you can effectively use your vFlash. A couple of quick gotchas you want to keep in mind. We just discussed that all the blocks of the vFlash cache are copied over. So the advantage of that is once your vMotion is complete, your cache doesn't need to be warmed up anymore. It's a hot cache. It's ready to go. It has all the blocks you care about. Your application is going to continue to perform really well the way it was before the vMotion. Right? The flip side of that coin, though, is that you need to copy all those blocks over, so it may take you longer to do that. Now, if some of you have 10 gigi networks, if you have multiple 10 gigi networks, that might be a blink of an eye. It might not matter to you at all. It may not affect your work. But in general, if you have slower networks or larger working sets to transfer, it can actually matter. Host maintenance mode operations rely on vMotions because they evacuate a whole bunch of VMs, so those could take longer. And the vFlash space that you have in your cluster can get fragmented over time. You can have some of it here, some of it there, it's all spread out. We don't have a way to balance according to vFlash. We don't do load balancing with respect to vFlash reservations today. Depending on how people use it, depending on the feedback we get, that's something we could consider in the future. And that's a deep dive that you can go find the video for, or the slides for, to understand this in a better way. The next topic is vSAN. It basically creates a distributed data store out of local data stores. And it creates the illusion of a virtual SAN, vSAN. Right? A host which doesn't have local storage can also be a part of a vSAN cluster. And all the blocks that you have are going to be duplicated across nodes just for reliability. DRS works with vSAN out of the box. The vSAN is in beta right now, by the way. But as you can imagine, till your local cache is warmed up, because your data is spread out across these nodes, till your local cache is warmed up, if you have an access to a data item, you might actually have to make a remote access to get it. So that's something you want to keep in mind. The last topic to talk about in this section is auto-scaling proxy switch ports. So this is actually a weird corner case, but we were starting to see an increasing number of customers hit it. So we decided to do something about it in the back end. This will not affect you. This is not something you have to manually go do anything about. It'll work transparently for you, but this will directly have an impact on some of your bigger hosts. Now, every virtual host, every virtual machine has a certain number of VNIC ports, right? It has a bunch of ports, virtual ports. The hypervisor has a bunch of ports. And the real hardware, your box, has a certain number of ports. These need to be mapped, right? So till vSphere 5.1, every ESX host used to support 4,000, 4K ports. And because every VM needs about 10 VNIC ports, you were limited to about 300-400 VMs on each host. When you started to hit about 300-400 VMs on a host, you couldn't admit any more VMs. HA wouldn't power on any more VMs on that host. DRS wouldn't move any VMs onto that host, right? Simply because there aren't enough ports. It's part of admission control. So it was a bogus limit, so we fixed it in vSphere 5.5. When you boot your ESX VM, we'll automatically discover how many ports this host can support, right? And for bigger hosts, the number turns out to be much bigger. It'll be auto-scaled up. And we are actually able to broadcast that number to VC and DRS And now admission control will magically admit a lot more VMs onto that same host that it couldn't do earlier. All right. So key takeaway points here, DRS and Vflash just play nice. Initial placement works. Load balancing will work as if it's soft-defined. And we have admission control with Vflash reservations just like any other reservations. vSAN and DRS play nice with each other too. And finally, proxy switch ports will let you use your big hosts much more effectively. All right, finally, we are at the future directions section. I'd like to point out that we had to fight tooth and nail with our legal department for every slide that you're going to see after this, right? So all of this is prototype stuff. All of this is fun stuff, stuff we do because we like this, and stuff we do because we think it's going to add value. You can talk to us, help us influence the way we develop these things, and give us feedback that will help us prioritize features. Okay, the first thing I'd like to talk to you about is the beginnings of network DRS. We do compute, we do storage. So we've started thinking about network DRS, and we've already had, since vSphere 4.1, right, we've had the ability to specify per VNIC shares and limits. You can actually say this VNIC has twice the number of shares as this other VNIC. And we've now started experimenting with bandwidth reservations, not just limits and shares. And anybody who's had to solve a problem, this problem or a similar problem before, knows that this is an unsolved problem. It's a hard problem to solve in computer science. How do you guarantee that you're going to get this much bandwidth on a physical NIC, right? Maybe for outgoing traffic, you can do something. For incoming traffic, you may or may not be able to do anything. You don't know what the external world is going to do. But we've been experimenting with this, and we're seeing some promising results. We've got some tie-ups with some professors who do research in these areas, right? So if we had these network reservations, they would work like other reservations. We'd make sure that if we were powering on a VM on a host, that there would be a physical NIC on that host, which could guarantee a certain amount of reservations to this VM, to this VM's VNIC, right? And if we were to make a vMotion, just like how a Vflash vMotion, with Vflash reservations would make sure that there were enough Vflash resources on the destination, like that, we'd make sure there were enough network resources, network bandwidth available on the destination before we recommend that vMotion to you, right? And what we'll also do is take all the physical NICs on a host and pool them together and do admission control against them. That lets you be a lot more flexible. You can have traffic move between physical NICs of your host. It's like a host-level network resource pool that you might have. What else do you want to see in this area? Is physical NIC even a problem? Is contention of physical NICs even a problem in your environments? Come and talk to me, right? Do you want network RPs at a cluster level, the way we have them for compute, right, of memory? So come talk to us. The next topic I'd like to talk to you about is static VM overhead memory. Again, this is one of those behind-the-scenes topic that it's not sexy, it's not glamorous. We don't usually talk about it, but it's extremely useful and extremely important because it spreads across all our solutions. And we're doing some very cool stuff here, so we thought we'd give you an insight into what engineers do, right? Static overhead memory is the amount of memory you need more than your reservation to power on a VM. You might have a VM which might have a gigabyte of memory reserved, but its overhead memory might be, let's say, 200 megabytes. So if we wanted to let this VM pass admission control, if we wanted to let this VM power on, we'd have to make sure that there was somewhere on a certain host 1 gig plus 200 megabytes to power this host on, power this VM on. Same thing applies when you move this VM around. When you take this VM here and you vMotion it to another host, we'd have to make sure that there's enough overhead memory headroom on that host, just like how we do with reservations. Several things change this number. You can have VM or host level config settings that can change how much overhead memory is going to be needed. A newer host might usually need lesser overhead memory than an older host. You might have bought a host, an ESX host 2 years back, and Intel or AMD might have given you some features there, right? And they might have newer features today that let us do things more efficiently and therefore need less overhead memory, right? Your VMs might have FT enabled or CBRC enabled, and all these are value-added features. But all these add a cost to the overhead that's required to run these VMs. It's a pretty complicated problem in general. And like I said, we use this number for admission control. Reservation plus static overhead must be guaranteed before we can do a power on or a vMotion. HA uses this, DRS uses this, manual vMotions use this, right? So it's used across the board. So I wrote a little article again with Duncan. It's available for you to read about some more nitty-gritty details. But all I wanted to do here is to share an encouraging result with you. We're not allowed to share anything more than one result at this point, right? So we took a VM which had 10 vCPUs and had 120 gigabytes of RAM, right, virtual RAM. How much overhead memory do you think this VM uses today? Well, anybody have a guess? Oh, come on, it's a guess. 1 gig. It uses 12.26 gigs, right? It's close to 10%. It's a pretty big number, right? In absolute terms, that's a lot of memory. And you need this to run a VM this size. We've had customers who wanted to put 2 such VMs on a 250 gig host, and they couldn't, right? So our new approach, any guesses for how much that takes? Sorry? Oh, you're a hard customer to please. Well, we need less than a gig, right? It's an order of magnitude reduction, and we're trying to do even more. There are very real reasons why it doesn't go down below this much. And if you have 120 gigs in your VM, needing less than a gig to keep track of it, most people, I think, would say not too bad. All right? All right, the final topic I'd like to end with today is something we've discussed in other forums. It's called proactive DRS. To talk about this, I'm going to tell you about how the DRS lifecycle looks like and compare that with the proactive DRS lifecycle. The basic premise is that DRS is a reactive algorithm. It reacts to changes in your environment and fixes stuff so that those problems are remedied. We start off by monitoring your inventory. We look at rules, we look at usage, we look at capacity, alarms, all of these things, right? And from that, we derive metrics, right? We're deriving growth rates, we're deriving rates at which your capacity is being extinguished. We're computing resource pool integrity, making sure all your parents have more resources than your children, stuff like that, right? We're making sure all the rules, the parameters, the constraints you've set are all not being violated. We check then to list out any violations we might have. We ask if the VMs are happy, like we've discussed our primary goal. Then we ask if the cluster is balanced. We ask all these questions in the evaluate phase. Then we remediate. We remediate it by fixing any violations that might be occurring right now. And if your VM is just unhappy, like we've discussed before, 3 ways of giving it more capacity: from the same host, on a different host, or from a powered off host in your cluster, right? So you remediate it, you fix up everything, and then you verify that everything is okay, and you do this loop every 5 minutes by default today, right? This is the DRS loop you all know and love. This is what the proactive DRS loop looks like. We still monitor your inventory, and we monitor it for months, years, whatever you give us. And we're able to predict cycles in your data. We're able to figure out what your VMs are going to do based on what they've been doing for a while, right? And we can use that to do preventive remediation. You can do stuff before it's actually needed. It's like magic. It's a crystal ball that's making vMotions when it's got no business to do it. But then you see a spike coming up, right? And then you're so happy that that vMotion happened. How many of you have nightly antivirus workloads or backup workloads or end of the month processing workloads? You know, every 2 weeks you've got some accountant that goes nuts with his software. I mean, you have these cycles. They're part of businesses, right? We all do things in reasonably predictable ways. And it's something that we've learned how to actually use. It's something we're working with very aggressively inside the company. We're trying to see if this can actually be made to work. The main motivation for this work is we don't want to clip VM demand, right? Which basically means if a VM is entitled to X number of resources, we want to make sure it doesn't lose, it doesn't get fewer than those resources. We've also noted that if you've got 500 VMs, all your customers come in a VDI environment and have a boot storm at 9 o'clock, everybody logs in, right? That you're not going to see a huge throttling of resources at that time. What we've also noticed is that when you have a very discontinuous jump in your workload, right, and that may only happen for 5 minutes, but the repercussions of that are felt for the next half an hour, next 1 hour into the life of the workload. Your workload continues to suffer because an hour back it didn't get what it needed when it started up, right? So these are the kind of things we're trying to fix. Remediation is much more expensive if you do it at the time it's needed. It's a prevention versus cure argument, right? If I can do some remediation preventively, I don't have to cure you when you're actually in high demand. We want to avoid spikes, like we said, but we also want to do proactive load balancing. You could have a whole bunch of opportunistic VMs that come in during the night and run some maintenance tasks for you, and they go away in the morning. But the rest of your VMs have not yet been spread out, and they're only going to be spread out when they actually start becoming active again. We know they are going to become active again. So why not use that data to start spreading them out up front, right? Preparing them for a spike that's about to happen. We use this for proactive DPM. I mean, people don't like to use DPM because they say, oh, when I want my capacity, I'm not going to have it. Hey, what if you do? What if you have it before you need it, right? And finally, even for things like initial placement or evacuation, when you're placing a brand new VM, I know nothing about that VM. I have no data, I have no predictions, but I know everything about all the neighbors of that VM. So I can make sure I place this unknown VM onto a sedate host where it's not going to be crowded out by its neighbors, where it's not going to be pushed out, right? So that's how we'd use proactive DRS. Right now, the way we're making it work is we've hooked it up with VCOps or VMware Operations Manager. It's one of our other products. This product is an analytics product. It monitors VCs and the VMs that are connected to those VCs. It collects stats, does analytics on them, and it does this thing called dynamic thresholds on stats, right? So this is a picture of the CPU utilization of a certain VM, and the blue curve represents the utilization. VCOps has only been observing this VM for a few days, I think, or one or 2 days, and it's already beginning to learn some patterns, right, about this VM. And you'll notice that the gray area represents the range that VCOps thought this workload might be in, right? The blue curve might be in. And you'll notice that the blue curve stops at some point, but the gray curve keeps going forward. And that area is the range of predicted values. That's tomorrow, right? That's what VCOps thinks you're going to need tomorrow, right? And proactive DRS is going to use the upper bound of that gray box as a conservative estimate of how much you're going to need, right? Keep in mind that this is not perfect. You see that the gray curve doesn't bound the blue curve fully. It doesn't smoothly follow the blue curve as you might expect it to, right? And this is something that we are actively working on with the VCOps team. This is a toy, it's a prototype right now, right? But when we actually come to market with a product like this, depending on how urgently you guys think this might help you, we might actually be able, we will be able to come up with a much better prediction system where you're actually able to predict the future and use that very, very effectively. We've got some very encouraging results so far, and we wrote you a fling, right? This is downloadable. We released this at VMworld US, right? So it's called proactive DRS. Go to our flings page and download it. You can actually play with proactive DRS today. You'll need vSphere 5.5 bits to play with it, so you'll have to download vSphere 5.5, right? And you'll need to have VCOps. This was the winner of our contest, Fling contest last year. One of our customers told us this might be a cool idea. This was already something we were thinking about, so we decided why not. So I wrote this Fling with an intern of mine, so I have my card. Send me any questions you have about it and we'll answer them. Right? It's a nice little toy, it's a nice tool. You can download it, it's a VM. It'll ask you for VCOps credentials. You give it VCOps credentials, it'll find out which VCs are connected to this VCOps. You give it any VC credentials that you might care about. And our Fling will go talk to VCOps for all the VMs in your VC, go to all those little gray boxes that are still predicted for tomorrow, take out values from that and stuff those into VC. And then all you need to do is go to your DRS cluster and say proactive DRS equal to 1. And then you'll have proactive DRS. So we'll at that point be using predicted demand from VCOps along with observed values from VC to make decisions about what to do. Right? It's a pretty cool tool. Give it a shot and give us some feedback, please. There's more details and assumptions on the Fling page. All right, so let me, oh, I was not supposed to be there. I'm going to, we'll upload the demo to the Flings page. In summary, VM happiness is the key goal of DRS. Load balancing is a mechanism we use to make this happen, to keep distribution fair, and realize that it doesn't have to be perfect for the VMs to be happy. New features in vSphere 5.5, managing number of VMs per host automatically, latency sensitive VM support, better ready time handling, and better handling of memory demand estimation. We interoperate with a whole bunch of new features, Vflash, vSAN, and auto-scaling ports. And finally, we have tons of cool stuff in our pipeline. You've already seen network DRS, overhead memory, and proactive DRS. We've got more coming, so stay tuned. That's all I have for you guys. Thank you so much.